All right, I think we can start here. Uh, Hello and welcome. This is the third lecture in the series, Get Wise, and today we are going to be talking about weather and climate. My name is Sanjay Limaye, and I'm a scientist at Space Science and Engineering Center and responsible for the Get Wise program. So we definitely appreciate your feedback. And as you can tell immediately that my color choice is not exactly what I had hoped for. They show up differently on the screen, on the monitor, but I hope you can follow a little bit. Today, we are going to be talking about weather and climate. And everyone talks about the weather, but it's very hard to do anything about it. And weather can mean different things. So I looked up the dictionary, and this is how the Webster's dictionary defines it. The state of the atmosphere with respect to heat or cold, wetness or dryness, calm or storm, clearness or cloudiness. That definition gives us a fairly good idea of what we are talking about when we mention the word weather. We can look at another source, and most of you are familiar with the GLOW program, I hope. If not, we can discuss it sometime later. And the GLOW program, which uses atmosphere as one of the protocols, defines weather this way. By weather, we mean what is happening in the atmosphere today, tomorrow, or even next week. Now, as you can see, these two different definitions give a different spin on the simple word weather. The globe defines it somewhat differently in that there is an observational aspect to it, there's a predictive aspect to it, and in terms of prediction, they're giving you an idea of the time scale, not just tomorrow, but even next week. Well, how do we do that? First of all, what do we need to have weather? To have weather, I think most people would agree, we need an atmosphere. We need a variable source of energy that can cause heating or cooling. And then finally, to make weather really interesting, we need a condensate. On Earth, it is water, but on other planets, other gases come into play, like methane, ammonia, or even carbon dioxide, which is a trace constituent in our atmosphere. But on Mars, you can actually have dry snow or dry ice. In fact, there are places on Mars where the weather is conducive enough so that dry ice falling on the polar caps would allow you to actually go skiing. Now we have many objects in the solar system, and what I am showing there is a composite of 12 objects. In the upper left, we have the airless Mercury, which has essentially no atmosphere to speak of. Now, some people may disagree with that statement in that they have detected sodium vapor coming off of Mercury. So that is a very tenuous atmosphere on the planet Mercury, which most people would consider airless. But nevertheless, we can actually detect sodium vapor around Mercury, sodium emissions. We don't know where that sodium comes from, and there's actually quite a bit of debate going on about the atmosphere of Mercury. Next, in the upper row, right here, we have Venus. Now, Venus, for many centuries, has been considered Earth's twin. It's about the same size, and people thought that it would be Earth's twin. Well, in the last 30 years or so, we have found out that Venus is far from Earth-like in that it is completely cloudy. Its clouds are made up of toxic sulfuric acid gas, and its surface, instead of being comfortable, habitable 60 degrees Fahrenheit, it's about 950 degrees Fahrenheit with a very crushing pressure at the surface of about 90 bars. That's about 90 times the atmospheric pressure that we have on the Earth. Earth, we know, is habitable. And then we have Titan in the upper right corner. Now, Titan is an atmosphere, is a moon of Saturn, which has an atmosphere which is thicker than our own. It is about 1.5 times as thick as the Earth's atmosphere. And people think that Titan's atmosphere now may be similar to what Earth started out with many, many years ago. In the next row, in the left column, we see Mars. This is a picture from the Hubble Space Telescope. And Mars has many qualities that make it very similar to the Earth. First of all, it has an atmosphere. It's about half as big as the Earth, so its gravity is not very high. And that makes it very hard for Mars to keep its atmosphere together. It has a day that's very comparable to ours, about 24 hours and 37 minutes. And more importantly, it has an actual tilt. That is, it spins on its axis at about 26.5 degrees. That's very comparable to the tilt of the Earth. Now, compared to the Earth, Mars takes almost twice as long to go around the Sun. That's its year. Its year is about 687 days compared to our 365 days for a complete revolution around the Sun. That means that as Mars travels around the Sun, it has seasons that are almost twice as long as the seasons that we have on the Earth. And those seasons are an indication to us that we can have weather on Mars. And we'll see some examples of that. In the next column, we have Jupiter. Jupiter is a gas giant. It's completely fluid, except for the very inner core, which is solid. And it's solid because of extremely dense pressures. But because it is fluid, it has the potential for weather. And in fact, right here, we see the famous red spot, which is believed to be a storm, an anticyclone that has been seen for over 300 years. Below the red spot, when you see the pictures blown up, and I won't blow them up here at the moment, you'll see other storms on Jupiter. In the next column, we have Saturn. With its ring system, it looks beautiful, but it's very similar in composition to Jupiter. Once again, it's a fluid planet, and once again, it has potential for weather. And in fact, we have seen huge storms on Saturn that are many, many times the size of the Earth itself. In the next column, we have Io. It's a small portion of Io as shown in this picture. And Io has an atmosphere of its own that's unlike any other that we know. Io is full of volcanoes, and all of its atmosphere, which is very thin, it's only a few microbars, a few millionth of the Earth's atmosphere. Its atmosphere is made up of sulfur dioxide gas that comes out from the volcanoes on the surface. And here's one volcano on the surface of Io. In the bottom row in the left, we have the planet Uranus, the third gaseous giant, about half as big as Saturn. Its composition is hydrogen and helium, like Jupiter and Saturn. And this is basically a featureless gas ball. We have seen the fewest clouds of any planet on Uranus. In fact, to date, we have seen no more than 24 clouds on Uranus. This picture was taken from the Voyager spacecraft about 15 years ago in 1986. And the total number of clouds we saw on Uranus was 7. And why the number is so small is a mystery, especially when you consider the next planet away from the Sun, Neptune, which is shown in the next column. Neptune and Uranus are roughly the same size, but on Uranus, we have great winds. We have many clouds to track, and we have determined the wind systems on Neptune quite well. So the question arises, if Uranus and Neptune are in the same part of the solar system, they both have similar compositions, why is their weather so different? In the next column, we have the last planet in the solar system, Pluto. Pluto also has an atmosphere, but it's dependent on its season. Pluto is so far away from the Sun that its atmosphere forms only when its surface begins to evaporate, to sublimate, that is, when it comes close to perihelion, and as the methane on the surface evaporates, it forms a tenuous gas. In the last column, slightly out of position, is a small portion of Triton shown in this picture. Triton is a moon of Neptune, which also has a very thin atmosphere, and it's peculiar in that it is the second example of, or actually the third example of a wonderful greenhouse effect, except this is a greenhouse in ice on the surface. And in fact, we have seen some wonderful tornado-like eruptions on Triton. We can have weather even on the sun. This is a three-color composite of the sun, and what we are looking at here are huge storms on the sun. These pictures are taken from the SOHO spacecraft, and they're available on the web. The sun, as we know, is mostly made up of hydrogen. Hydrogen is a gas, and one of the key ingredients for weather is to have a gaseous object, a gaseous entity, and the sun has plenty of it. So we can expect weather on the sun. There is one important difference, however. The second ingredient for weather was a source of energy. The sun provides its own energy, that is, it is internal energy. It is not getting its energy from any other object, unlike the planets. So we can expect that the storms on the sun or the weather may be a little bit different. Now, here's an example of what happens when an atmosphere, such as on the Earth, receives energy from the sun. What we are looking at is a global composite that shows cloud systems, or fronts as we call them, and oceanic areas and land surface areas. Now, if you focus your attention in the middle of the picture, there's a very dark area. This is the African continent. And then when you note that this picture was taken at noon on April 4th, and that's noon universal time, we can realize that this is basically taken at local noon. So this is local noon here, so this darkness can be attributed to the heat, which is most intense at local noon. Now, if you follow this in time lapse, which we can on the web, you'll see that area of high temperatures move with the sun. This is better shown in the next picture, which is a composite of data from surface weather stations, ocean surface temperatures determined from satellites, ships and buoys, and satellites. And once again, this shows basically the same thing, basically the effect of the sun in defining the conditions on the Earth. Now, the sun also plays a role in weather systems such as the oceans or the El Nino phenomenon. The El Nino has been in vogue, at least the name, the phrase is well known now in colloquial usage. Now, what is El Nino? El Nino is a combination of the effect of winds on the ocean, and when the winds here in the upper half, we have the winds that blow equatorward from the south in the eastern equatorial Pacific, and they go westwards, which is shown by this pink arrow. Now, with these winds blowing westwards, what happens is that the water on the ocean surface gets pushed westwards over here. Now, at the top of the ocean, the surface waters get heated and they get warm. Underneath, we have cooler water. So the warm water gets pushed westwards by these winds. And El Nino is the phenomenon when those winds die down, all the water that is piled westwards splashes back to the east. That cuts off the supply of the nutrients from the cold water underneath, and the fish disappear, basically. So this is the El Nino phenomena, and this is one example of how the weather is affected not only by heat from the sun, but also by the winds which are caused by the heat from the sun. And in this slide, this is an example. In the upper slide, here are the winds depicted from 0 to 10 meters per second here. In the bottom, we have a cross section shown as a function of time from 1981 July through 1982 June. And this is the ocean depth in the ocean. The top is 0. This would be the ocean surface. And during a normal year, the winds are blowing westwards and the water gets piled up here. And so cold water from underneath is able to rise a little bit to the top along the west coast of South America. On the right, in the right panel, in the upper right here, in about 1982's December, when the winds subsided, the water came back and the warm water appeared where the cold water used to be. And this is one example of El Nino. This was the strongest El Nino in history, and it shows the interplay between the winds, the oceans, and the sun. This is another version of that. I think because we are running a little bit late, I won't dwell as much on this particular slide, but once again it shows the monthly winds. These are shown in arrows here in the top. The colors show the sea surface temperature, and on the bottom are seen the El Nino anomalies. This is what a normal year is supposed to look like. Cooler temperatures at about 120 degrees west in the equatorial eastern region of the Pacific, and warmer temperatures in the west. Now, a phenomenon like that has impact not only on the conditions in that region, but globally. And why that occurs is something that we'll explore. Now, in this picture, we see a mosaic of water vapor. This is once again made from space, from satellite observations, and it shows the condensate. To make weather interesting, we need a condensate, and water is a good condensate. Water can exist on the earth, at least the conditions that we have, in 3 phases. It can be liquid, it can be solid, like snow or ice, or it can be vapor. And it's that phase change from solid to liquid to vapor, or the other way around, that makes weather interesting and challenging to predict. Now, to go back to the Webster's dictionary, we'll recall that one definition of weather was the difference between stormy and calm. So what is a storm? And according to the dictionary, it's a disturbance of the atmosphere marked by wind and usually by rain, snow, hail, sleet, or thunder and lightning. Well, we all have experienced it, so I don't need to describe what this means. But how are they produced? And can storms occur only on the earth? The answer is no. Here we have a sequence of 4 images from Mars. It's a storm system near the North Pole of Mars. This was observed last May, and if I can manage to do it, I'm going to try to show you a movie of it. I don't know if that movie shows up in your screens, but there is a link to it on your the notes that are given on the web. What you see there is a rotating Mars. Oops, I shouldn't have done that. And actually, that was the wrong clip that I showed. This is the clip that I wanted to show you. Right here in the upper corner is the movie of these pictures taken uh, on Mars. Anyway, I guess it went away. I won't dwell on it. You can explore that on the web. It'll look much more interesting than on the television screen. So the point was that storms can occur even on planets like Mars. And all you need are the same ingredients, that is an atmosphere, a condensate, and an energy source. Here's another example of storms, and this is Jupiter. Jupiter has a condensate which is different. Now, you have to remember that Jupiter's atmosphere is mostly hydrogen and helium. Now, when you add water to it, it normally tends to sink, even in vapor form. On the Earth, water vapor changes the density of air. When you add moisture to dry air, the density of that new mixture is less than that of dry air. And this is because the dry air has a higher molecular weight than water vapor. It's because of the chemical composition. And so moist air tends to rise when it's brought in contact with dry air. This is what happens in a storm, that you're bringing in moist air that mixes with dry air. The moist air rises because of the density difference. As it rises, it cools, and it is the basis for precipitation. On Jupiter, the situation is different. When you add a condensate, because hydrogen is the lightest gas, almost any other compound that you can add to that gas is going to be heavier. So the condensate on Jupiter sinks, it doesn't rise. And that's the interesting aspect of Jupiter. And despite that, we see storms that look very similar, as you know, as shown in this picture. Here is a thunderstorm-like cloud on Jupiter. There are 3 panels. These are taken from the Galileo spacecraft. On the bottom panel are shown the winds that show the circulation of the atmosphere in those areas. Here's the cloud system, and in fact, we have detected lightning in areas such as this, and the top one is just a color composite. On Earth, we have seen storms of all different kinds. Here's a beautiful composite taken from Galileo spacecraft. In 4 different views of the Earth, we can see the different continents. In the upper left, we have the South American continent. Here we see Australia in the upper right, the Pacific Ocean, and here we have Africa. All over the Earth, we see storms. So how does this come about? We have seen that what we need for weather is an ingredient like an atmosphere, a condensate, and a heat source. In other words, the weather is a cause, or I should say that the atmosphere functions like a heat engine. Think of the weather as the byproduct of something equivalent to your automobile engine. You provide heat, that's the fuel. You have a radiator, that's the top of the atmosphere, and the work is done by the atmosphere through winds and by the oceans through the currents. So what changes weather then? Temperature is one aspect of weather. So we can consider what changes temperature. Well, heating is primarily the reason or the factor that controls temperature. Since the sun is the primary source of heating, for the inner planets anyway, the energy absorbed by the Earth atmosphere-ocean system is the fuel for the atmospheric heat engine. So if we can change that heating or cooling, then we can expect changes in the weather. By the same token, we can change the atmospheric composition, and that can lead to a change in the weather. And how do we change the atmospheric composition? Well, we have seen examples of it. We can change the amount of water vapor in the atmosphere. We are changing the Earth's atmospheric composition slowly by adding carbon dioxide and other gases like methane. And why is the change in the atmospheric composition important? It's because certain gases or chemicals absorb energy in specific regions of the spectrum that are important. Now let's consider how heating and cooling can take place. Basically, heating and cooling are aspects of transfer of energy from one object to another. And we can exchange energy between oceans and the atmosphere and the solid Earth. And there are three ways with which this energy transfer can take place. And those of you who teach physics are already familiar with it. I just want to elucidate them here for the sake of completeness rather. The three processes are radiation, convection, and conduction. Every object emits and absorbs radiation, that is electromagnetic radiation, whose spectrum is determined by its temperature and its emissivity. Most of the sun's energy arrives at the Earth through the process of radiation. The sun radiates at a very high temperature and it has a characteristic spectrum. Radiation does not need any intervening medium. It can travel through space. Examples of radiative heating or cooling are cooling that you notice on clear nights, especially dry nights, or warm nights when it's cloudy. The greenhouse effect is another aspect of radiation process. Now here's what the solar spectrum looks like. This is a spectrum that's been broken up into different strips so that we could show it to you in a picture. And it's the visible spectrum. It goes from, it's basically the rainbow, from the red to violet. Now if you notice this picture carefully, you'll notice that there are some dark lines, like here. This is called the sodium doublet. And I gave away by calling it the sodium doublet that this is a signature of the presence of sodium in the solar atmosphere. These dark lines are called Fraunhofer lines, and they are absorption lines. And they are characteristic signatures of different elements. This doublet here is sodium. And there are other lines that indicate presence of magnesium, iron, and all the other elements that we know of. What this indicates is that even in the visible, if we have those elements, they can absorb visible light directly. This is what the spectrum of the sun looks like. The red line shows the actual spectrum measured from the sun, and the yellow thick line indicates our approximation to it, which is based on a black body temperature of about 5800 degrees Kelvin. Kelvin is a different scale of temperature. If you subtract 273 degrees from it, then you get the Celsius scale. And as you can see, the 5780 degree Kelvin profile of the black body matches the solar spectrum very well. The departure from that, especially at the shorter wavelengths here, and the scale is given at the top. This is 1 to 2 microns. That departure is due to the fact that not all parts of the sun are at the same temperature. And this is an important point that will become clear later on when we look at the radiation emitted by the Earth, shown in this figure. There are two lines shown here, basically a thick green line and a wavy thin line, which is also in green, and that seems to go all over. Well, the green line is a black body computation of the spectrum for a body at a certain temperature of about 250 degrees K. And the green wavy line is the actual spectrum of the Earth. These gaps are due to the presence of carbon dioxide. These are the absorption windows. This is the 10 to 15 micron absorption band of carbon dioxide. And there's another band that is important between 8 and 10 microns due to ozone. And water vapor is only weakly absorbing in this region. Now we know that Mars also has an atmosphere that is made up of carbon dioxide, and so we can compare what Earth and Mars look like. And I apologize, let's see if we can change the brightness. Maybe this picture will show up a little bit better. Maybe not. When you look at the PowerPoint slide, it'll appear better there than it does on the TV screen here. And I apologize for it. This is the only graph of its kind. It is very difficult to get a spectrum of the Earth as complete as this from space because we just don't have that kind of instruments. This figure was obtained from a spacecraft that was on its way to Mars, the thermal emission spectrometer, which flew on Mars Global Surveyor, and right now it is collecting data on Mars. What we are looking at here are basically two lines, a blue line and a red line in the upper figure, which shows Mars. And the red line, the red curve here that I'm trying to trace, shows the temperature at 290 degrees Kelvin on Mars, and the bottom one, the blue one, at 180 degrees Kelvin. And this dip here in the actual spectrum is due to the presence of carbon dioxide. Now, if you compare Earth in the lower part, we see the same absorption band due to carbon dioxide and ozone, and right here is the water vapor. And the blue curve here is at 215 degrees Kelvin, and the red curve in the bottom figure is at 270 degrees Kelvin. And those two curves match the spectrum of the Earth very well. And by comparing those two, we can tell how much of the radiation is coming from which part of the atmosphere. Because as we know, the temperature changes from surface to the top of the atmosphere in a somewhat predictable manner. Now, the heat coming from the sun obviously goes into different processes. If we here we have the sun, and in this diagram, 100% of the incoming solar energy hits the Earth, or at least that's how we want to do the energy budget. That absorbed by the land and oceans is about 51%. But before it gets there, about 6% gets reflected by the atmosphere, about 20% gets reflected by the clouds, and about 4% reflected from the Earth's surface. Some of it is absorbed by the atmosphere, which is about 16%, clouds 3%, and then the energy that is absorbed by land and oceans, it is re-emitted by the Earth at a different temperature. Remember, the sunlight coming in is coming in at roughly 6,000 degrees Kelvin. Earth is emitting it at a different temperature. When that energy is emitted by the Earth, it gets absorbed by certain compounds in the Earth's atmosphere. And those active gases are carbon dioxide, methane, and water vapor. Even snow can act like a greenhouse material in that it's reflective in the visible, but it absorbs some infrared wavelengths. And this aspect is important on an object like Triton, where we have solid-state greenhouse. So this is the greenhouse effect. It is caused by the selective absorption of radiation in the infrared and transparency to visible sunlight. And it's an important process in determining Earth's climate and weather. Now, the second process of energy transfer is convection, and this is transfer of energy by the physical movement of matter. It's a process governed by properties of the material that is moved and of the material through which it moves. It seems like a strange definition, but basically think of it like a helium balloon in an atmosphere. When you let go of it, it rises. If that helium balloon was at a different temperature, then it's carrying heat. And this is what is known as a convective process. This is what gives rise to a thunderstorm. Examples are a boiling pot of water, volcanic eruptions, thunderstorms, and they're all caused by localized heating or cooling. And finally, we have the third process of energy transfer, conduction. and it's the transfer of energy between a bulk material or across a surface through physical contact, and it's governed by a property of the material called conductivity. Now, conduction is not so important in determining the Earth's weather compared to radiation or convection, but it can be occasionally significant, especially in the northern climates. It's basically heat loss through contact with wind, or wind chill as we know it. It can also determine the frost depth in subfreezing weather, and it's important for a certain community, basically the grave diggers, or people who have to work on drainage systems or water mains. The city water works department people care very much about the depth of frost. Now, going back to what changes weather, we have seen that if we can change heat, we can affect weather. Well, what about moisture? Moisture affects the buoyancy and heating of or cooling of the atmosphere. So moisture acts two ways. First of all, it can change the density of the air mass that it gets mixed in with. And because of its specific absorptive properties in the infrared, it can also impact the heating or cooling of the atmosphere. Humidity or moisture, as we know it, can exist in three forms: vapor, solid, and liquid. Phase changes are accomplished by heat exchange. In essence, to melt ice, you have to supply heat. To form ice, you have to extract heat, and that amount is roughly 80 calories per gram of water. Similarly, to make water evaporate, you have to apply heat. And by the same token, if water vapor is to condense, it has to give up heat. Somehow you have to remove heat. Well, formation of clouds is a process. That's a phase change process. And so to form clouds, we have to have heat exchange. In fact, this is the key to the maintenance of the hurricanes, in that the latent heat release in the upper atmosphere is what provides the energy to the strength, or that determines the strength of a hurricane or a cyclone. And finally, wind can change weather also, and I don't quite know where to put it in terms of the different classes of processes that we can have to change the weather. And that wind is the result of atmospheric pressure changes, and it, in a sense, they are an artifact of the weather, and yet occasionally winds can impact regional weather also. They can change the weather locally and regionally because they depend on air masses and density variations in the atmosphere. And examples are monsoon circulation is basically a wind circulation, sea and land breezes. It depends on how comfortable one can be near a seashore or a lakeshore on a hot summer day. Density winds, which are basically drainage winds that occur at night in the mountains, or Fen, which is basically the same kinds, except they are usually driven by large-scale flow in dry climates. So we have arrived, or at least summarized, the recipe for weather change. We can have changes in heating or cooling. Now they can occur on the Earth or on any object by changes in orbit. That is, insolation changes due to the geometry of the heat source, in this case the sun and the planet. As Earth goes around the sun, its distance to the sun changes, and so that causes a change in heating. It can also have diurnal changes because of the Earth's rotation. We have day and night differences, and those are important in desert areas. The insolation changes along coupled with the tilt of the object or a planet give rise to seasons, and they also cause changes in heating and cooling. Well, we can create change in heating and cooling also by creating changes in surface properties. That is, the reflective properties, or the ability of a surface to absorb heat. Deforestation, urbanization, or topography are different aspects of how we can create that change. And finally, changes in the atmospheric composition. We can change the amount of greenhouse gases and change the impact of heating and cooling in an atmosphere. Now, we shouldn't exclude changes in the heating right at the source. Earlier, we saw a picture of the sun with a number of storms on it. Well, those storms produce a change in the amount of heat it gives out. This is a plot of the total irradiance, the total energy emitted by the sun. And actually, let's focus on the bottom, which is a much longer record that goes from 1978 to 1999. And it shows a variation in the output, which is measured in watts per meter squared. And the black line, which is an average, is fluctuating from 1366 to as high as 1367 or a little bit higher. That's a tiny difference, but nevertheless, that difference can be significant over a long term. And this is only over a period of about 20 years. Over the sun's lifetime, this curve will change dramatically, and that will surely cause some changes in our climate and weather. And here's an example of how that occurs. And on the links that are given to you on the notes page for lecture 3, you'll find links to movies of the sun where you can see eruptions or prominences or coronal mass ejection that can come the way of the earth and also impact us in other ways rather than directly. Here I'm listing a few sites which can give you information about weather on Mars in particular. And we are running out of time. I do want to give you some time for some questions, so I'm going to go through this somewhat quickly now. The second topic I was supposed to discuss today was climate, and we haven't had a chance to get to it. So quickly, according to the dictionary, the climate is the average course or condition of the weather at a place over a period of years as exhibited by temperature, wind velocity, and precipitation. And let's look at a second source or get a second opinion on what we mean by climate. And according to Globe, by climate, we mean weather over time. If that's the case, then occasionally we can have a situation where the weather is the climate. If the weather is the same every day, then the climate and weather are the same. Supposedly, according to the song, it never rains in Southern California. And so the weather in California on any given day is close to its climate, at least for this period. On Venus, with essentially no seasons because no actual tilt, no land-ocean differences, uniform cloud cover, the weather never changes, or it shouldn't, because there's nothing changing the heating or cooling of this planet. And hence, the weather on Venus is its climate. In fact, looking at the surface, we know that there are wind streaks that have been there for about 500 million years. That's how stable the weather can be on Venus. It is the climate. To summarize then, here are some key concepts. Weather over time is climate, and so to better understand the climate, we must develop a better understanding of weather and the factors that control it. Climate over a very long period, thousands and millions of years, can be very different because the conditions do change. Earth's orbit over that period is not the same as the orbit that we are in currently, and hence the climatic conditions on the Earth have been different in the past and they will be different in the future. A study of the past climates requires a good knowledge of the past physical conditions. And this is one of the hardest things to do because we don't have records. We didn't have record keeping in the prehistoric era. And we had to determine it scientifically from the effects of climate on other things such as tree rings or ice cores and things of that sort. Earth's orbit, its surface, and its composition, at least of the atmosphere, have changed since the beginning through complex processes such as continental drift, subduction, asteroid impacts, and more recently, human activity. And so we can look forward to changes in the climate. And finally, weather is global. The chemofluorocarbons found in the Antarctic weren't emitted in the Antarctic. They came from the northern hemisphere. Most of the world's population is in the northern hemisphere, and most of the CFCs in the Antarctic came from the northern hemisphere, thousands of miles away. Weather is a result of physical processes, and hence, if we understand the physics of weather, we can predict weather because now we have good computational skills and computational power. And in order to be able to predict weather, we need good physical or global observations because the weather forecasting basically requires a set of observations from which we can begin. Now, somebody had asked a question for what the worst case scenario for climate change or global warming is going to be. And I'm going to answer it this way. Venus provides a good warning for adding too much carbon dioxide or other greenhouse gases to the atmosphere. And this is over millions of years. Venus, as we now know, is extremely hot, about 950 degrees Fahrenheit at the surface, at the equator, and it's the same temperature near the poles as far as we know it. Earth and Venus started out about the same, and how did Venus get so hot? That's the question that we want to ask, and we don't want to end up in the same position as Venus, at least not in the immediate future. In the long run, and that's a few billion years, Earth's days are numbered. We're impacted by the aging of the sun, and when it goes, the Earth goes, because we know the sun is going to head towards becoming a red giant in about 3 to 5 billion years. And when that happens, essentially the sun will start expanding. First it will engulf Mercury, and then it will envelop Earth, and hopefully by that time we would have found a new place to live. Thank you. With that, I'll end my formal lecture, and I hope you enjoyed this somewhat different overview to weather and climate than what you might have been expecting, and I'll be happy to answer any questions.
No, this was good. We spent about 12 weeks on weather.
Great.
There's a lot of stuff here that I can add to the curriculum, especially the stuff on the other planets.
Right. Now, if you are able to get to the web, there are many links that I have provided about weather on Mars, some information about weather, or at least what we know about weather on Jupiter and Venus, and even Neptune. There's a movie link. And I'll try to add some more information about temperatures and winds. I was not able to get the slides scanned that show the wind profiles on different planets. We do have that information. That's basically what I do, study the weather on different planets. And so I wanted to give a comparative view of weather rather than the traditional view, especially if you have been teaching it, then you already know some of the things. And right. Our intent was to give you the core background behind some of the things that you teach.
Yeah, no, you presented them in a different way. The ingredients, I guess when you think about it, it makes sense, but that's not a way we looked at it before.
Right, and that
the atmosphere, the variable energy, and then the condensate.
Mm-hmm.
So that's something I can present next year.
Wonderful. And I think it's something that we don't traditionally think of weather because, like I said, everyone talks about the weather, but nobody does anything about it. But I think before we can do something about it, we have to really understand what is it that it implies. What do we have to change?
Yeah, can I ask you a question about El Nino?
Please do.
Okay, we have the winds going to the west and backing that water up, or
right.
pushing it that way, the surface water.
Mm-hmm.
Then the winds die down, that water comes back towards South America.
Essentially, right.
And then It cuts off the nutrients from below.
Yeah, essentially what happens then is that that warm water that is sitting near the South American coast cuts off the upwelling of colder water
Okay.
and colder water from deeper depths of the ocean near there. And it's the colder, cooler waters that have the higher nutrients. And so what happens is that the fish lose their supply of nutrients, and that's why they die down.
Okay.
And typically this happens in that part around December, and that's why it's called the El Nino, the Christ child.
Okay. Yeah. Right.
And just to add one point, the fish may either die down or also they may migrate. That's an important point to keep in mind. But they move to a different location, and this is when the phenomenon of El Nino was first noticed. It affected the fishing
Right.
availability along the coastal areas.
Right. That's an annual thing, but that seems to have cycles.
No, it's not an annual thing at
An
all.
annual thing.
No, in fact, I think it's only in the last, I would say, maybe what, two or 3 decades that we became aware of it, of the physical basis for it. I mean, the fishermen in Peru and
In the Latin American area, they have been aware of the phenomenon for many decades. In fact, for many hundreds of years since the Western colonization in that particular area. And so the phenomenon El Nino is affiliated with Christmas time, period. And then once again, the symptomatic effect that the local population noticed, once again, was the change in the availability of fish that they used for their food resource. And it really has only been measured in the last several decades by the scientific community using satellite data, etc.
Okay, I think today was the first time I heard about the winds. I guess either if I didn't notice that before, or it was the first time I heard the winds mentioned.
well, it's only recently that we could actually measure winds on the Earth's surface. And let me see if I can show you a movie clip that shows that. Let me just find it here. We have a spacecraft called QuickScat, and the QuickSat satellite is able to measure the winds on the surface of oceans using radar. And those winds basically give us the kind of information that is crucial for determining what kind of a situation we are going to have with respect to El Nino. Let's see, I'm not sure if I have it. I have a CD. The link is there on the web.
Okay.
In fact, there's a link. I mean, you can basically look at the real-time winds over different parts of the world oceans, and there are sections of it given in different areas. I can't seem to locate it right on my laptop right now quickly.
Okay, that's fine.
Uh,
Yeah. I have a question too
Sure.
about global warming and climate. I
Okay.
was the one that asked that question that you answered
Okay.
about the worst case scenario that some kids were wondering, and I just kind of worded it that way. Global warming, can you the way you answered it with comparing us to Venus,
Right.
talking about long periods of time, but there could be short-term impacts too, couldn't there? Depending on
There
what,
can be,
what
yeah.
actually happens as far as the temperature.
Right. And there's one link, and I'm showing you a graph of the carbon dioxide. It doesn't show up too well on the screen, but there's a link to it on the web pages, and that shows the variation of carbon dioxide that goes from roughly 150 parts per million by volume to over 260 parts per million. And this is a record from ice cores taken in the Antarctic at a Russian station, and the variation is over roughly 450,000 50,000 years before present.
Okay.
Right here on the right hand side, it is 450,000 years before present. So the present would be about here, and actually a few thousand years back. I don't know, about 6,000 or 10,000 years back. But fairly large fluctuations in the amount of carbon dioxide have occurred in the past.
Uh-huh.
And this is what gives rise to the debate about global warming. And in fact, there's a very nice curriculum activity about global warming that engages the students in finding out what happened in the past and what is happening now and what may happen in the future. Now, you have to realize that this intense scrutiny about global warming is fairly recent in that we
Right.
really have not been uh, looking at global warming in that detail for very long. And so we are
Yeah.
learning about what happened in the past. Events like volcanic eruptions can cause changes. We also know that carbon dioxide is fixed by vegetation. So large changes in vegetation can, of course, affect the amount of carbon dioxide. So if you have deforestation, that will adversely impact the amount of carbon dioxide in the atmosphere. That is, it will go up.
Go up.
By the
Right.
same token, if the rainfall increases and the entire Earth becomes green, then there'll be more absorption of carbon dioxide by the vegetation, and so it might lower the carbon dioxide. And that's what makes forecasting very difficult in that we can't predict if 10 years from now you're going to have a drought condition or not. And that drought, the timing of that drought has to be right also, because if it occurs in the growing season, then indeed it will impact the amount of carbon dioxide taken out from the atmosphere. Whereas if it happens in the wintertime in the north, when you normally don't have any vegetation because it's either covered with snow or it's fall, then it won't impact the carbon dioxide amounts very much at all. And the role of the oceans is another story here. We don't know how much carbon dioxide gets absorbed in the oceans.
Mm-hmm.
And these are not easy measurements to make, and I think that's what we are trying to accomplish.
Yeah.
And certainly going to the ice cores, I mean, we know that there have been wild changes, although what does not show up on this graph is that even with these changes, there's a dramatic change in the last 100 years in the amount of carbon dioxide, in that it's about 100 parts per million more. It's about 30% more than it is. And when you plot it over a longer period, then the increase becomes almost exponential in the last 300 years or so.
Right. There almost seemed to be a pattern to that ice age.
There is a pattern,
Uh,
and that is probably related to some of the cyclical patterns in the Earth's orbit. But I'm not so sure. I don't think we know for sure. I mean, there
okay.
could be other changes. It's possible that, uh, I mean, when you consider those kinds of timescales, then they are comparable to the timescales of asteroid impact. And asteroid impacts are a big story here because a large impact, such as the one that killed off the dinosaurs that occurred
Right.
65 million years ago, that would have changed the Earth's composition, or at least the atmospheric uh, situation for a long time, of at least 1 to 2 years or even longer.
Yeah.
And so it's the external events like asteroid impacts or volcanoes that we don't know much about exactly when they occurred in the past. I mean, we can tell some of them if they left a lot of debris, and we can date them, but it's not always easy.
Yeah. Uh, One other question. I don't know if you can answer this or not, but I one time heard somebody say that if the climate changes
Hmm.
worldwide, there'll be winners and losers. And I think what they mean is maybe a place that was dry is going to get water, and a place that was wet is going to not get as much rain. Or would it be more global? In other words, the whole planet would get drier, the whole planet would get wetter, or
No, well, global warming, first of all, implies that the whole planet is going to get warmer as a whole.
right?
But that doesn't mean that all the parts of the globe are going to get warmer. In fact, the northern parts will get a lot warmer than the equatorial parts. And so I think now, these, you shouldn't treat these as fact, but
Yeah.
more as guidance.
Right.
Most of the climate models seem to predict that the uh, latitudes around 50 to 60 degrees north will get warmer, and the ones somewhat at lower latitudes will get slightly cooler. And there will be differences in the amount of precipitation. And I think they have to do with the continental differences. And there is a plot, I mean, we can sort of get a feel for it by looking at what happens in El Nino years.
Right.
I think continents like the Asian continent, they get to be a little bit drier. They get less rain. So certainly India got less rain. Now parts of the US get a lot more rain, but other parts get a lot less rain.
Right.
And one consequence of global warming is that that pattern is going to change quite a bit. And there are, go ahead.
And one thing I was going to add that relates to your original comment is that I think what they're implying is the socioeconomic impact of such a change
I
in
think so too.
typical climate patterns. And of course, if we talk about the Asian continent getting significantly drier, if we consider a significant proportion of the world population is there, that has a significant impact on the food supply and availability for that particular continent. And certainly that'll be of global concern.
Right.
Yeah, and I think more recently we're also becoming aware of how much the sun can change. And I think
Hmm.
over the last few hundred years there have been measurable changes in the strength of the sun. And I think uh, our climate models are now becoming a lot more sensitive to that aspect, and we'll learn more. But certainly, I think we need better observations. Anyway, I think we are only a few minutes away from when we lose our link. I
Okay.
want to thank you for your interest, and do send us some feedback about the future topics that we want to cover. I think the next lecture is on soils, the good earth by Professor John Norman from the Soils Department on this campus.